Associated Universities, Inc. in recognition of outstanding contributions to astronomy. We are pleased to have Professor Irwin Shapiro of Harvard University, the director of the Harvard-Smithsonian Center for Astrophysics, as this year's Jansky Lecturer. He has received numerous awards and honors, including both the Danny Heinemann and Dirk Brouwer Awards of the American Astronomical Society and the Charles A. Whitten Medal of the American Geophysical Union. He is well known for applying the techniques of radio and radar astronomy to interesting problems in astro, geo, and planetary physics. Tonight he will speak on the subject, Reckoning the Size of the Universe Through Gravitational Lenses. Please welcome Professor Shapiro.
One more to click on. Good.
I have enough mics now. Well, it's truly an honor for me to be associated with the name of Carl Jansky, who made one of the most profound discoveries of modern times, namely that radio radiation hits the Earth from outer space. It's all very obvious to us now, but 60 years ago it was a mind-boggling fact. So important a discovery it was that no one realized, or practically no one realized at the time, that it was an important discovery. In particular, the professional astronomers all but ignored it. But Jansky knew that he had made an important discovery, and unfortunately he didn't live long enough to see just how it finally became recognized as so important and so fruitful to our understanding of the universe. I took the occasion to read a biography of Carl Jansky in preparing for this lecture, and I discovered a very mild parallel with my life, namely his discovery came at the time of the birth of his first child, and my best idea came at the time of the birth of my first child. So I felt there must be something here for at least one or two PhD theses in sociology, if not in psychology. But that will be the subject of another lecture, and I'll leave that for now. Many of you may notice there's some apparatus here, and there's also a TV, very fancy TV over there. And you'll find under your seats a switch so that if the lecture gets too boring, you can turn on the TV and watch Masterpiece Theater or Sesame Street. The only trouble is you'll all have to agree or the set goes wild. So anyway, enough. I have to bring this along with me. So now we will begin the lecture proper, and I think I have remembered the title correctly, Reckoning the Size of the Universe Through Gravitational Lenses. I intend to go through this lecture in more or less an historical fashion, giving you the history of gravitational lens research, history in which I will only tell a few white lies, no big ones if I can help it. Also, there will be no revisionist history. That's not my style. I may or may not be politically correct. That'll be up for you to judge. I'm also going to use the case history approach in showing how gravitational lenses, at least in one case, can be used to reckon the size of the universe. And then at the end, I'll give you a few prospects for how we might improve things. But one thing I will mention at the outset, and that is the story is not finished. It ends up, that is, today will end up in a complicated situation where we don't know the end. And in science, one almost never knows the end. It's just, you have to recognize in science one doesn't have revealed truth. And you might also notice that I used a gerund in the title of the talk just to indicate that it's an ongoing process and it's not something that's cut and dried and ready for the the textbooks. Okay, first for some history. I've broken history down. Looks like I'm breaking down. I broke history down into three parts: ancient, modern, and what I call current events. The story here really begins with Newton back in 1704 when he produced his second most famous book, Optics. His first most famous being, as I'm sure you all know, the Principia. In Optics, he raises the question as to whether light would be affected by mass, and in fact the trajectory of light bent by mass, more so if it were closer to the mass. He raised this question, but apparently never did any calculations to see what his theory in particular would have predicted about such an effect. Nothing much happened as far as the historical record is around to say until almost 80 years later, when the Reverend John Mitchell in England — by the way, reverends didn't have much to do those days in England in their major professions, and they spent a lot of time on science. And John Mitchell was, in fact, a first-rate scientist. I'm not sure how good a reverend he was. There's not much in the historical record that I found that tells me. But anyway, he had this neat idea that suppose you had a heavier and heavier mass, such that light, the effect of it on a light ray would cause it to bend. Okay, and if you made it heavier and heavier, it would bend so much it may never get away from the mass at all, i.e. a black hole, which he didn't name, but he had the concept really well thought out back in 1783. The first one who did a detailed calculation of how light would behave in the vicinity of mass was a fellow by the name of Soldner in Germany, but nobody paid much attention to his calculation, and certainly no one thought about whether one should do an experiment to see if actually nature behaved that way. You know, there's theory on the one hand, but there's also experiment measurements to see if the theory is actually the way nature intended. Anyway, nothing much happened for over 100 years until Einstein came along and developed his theory, which superseded Newton's. Einstein was a fellow who always went back to fundamentals. He liked to understand things from their very basic nature. And he had a problem with Newton's theory of gravity. Newton's theory of gravity had the following property, that the force that one body exerts on another is done so instantaneously. That is, suppose I have a body here attracting a body here, and I move this body. This one feels the fact that this is moved instantly. Very strange, said Einstein, considering my special theory of relativity, which said nothing, well, more or less, nothing moves. I told you I tell white lies. Nothing moves faster than the speed of light. So if nothing moves faster than the speed of light, how does this body know that this body is moved instantaneously? So he set about developing an entirely different theory of gravitation, so different that at first glance you don't see any connection at all with Newton's, although it reduces to Newton's in certain cases. So let's see what happened at that time when Einstein did this theory. It was back in 1916 approximately, and he realized, as did others, that one could test his theory, which, by the way, predicted the bending of light by mass to be twice as much as Soldner's calculation based on Newton's. So he had a new theory of gravity that in certain limit agreed with Newton's, but in other cases gave quite different results, namely a factor 2 different in the amount of bending you could expect a mass to exert on, or to affect a light ray. So the idea was, well, let's see if this bending really holds true. Let's look and see what the sun does to starlight. You ever try to look at the sun? I mean, how shall I put it? Yes, you try to look at the sun. Have you ever tried to look at stars when the sun is up? You don't see them too well. And well, you can see them at night, but then the sun is nowhere around, so it's very hard to see how the sun is going to affect the path of the light from stars. But there is one time when you could do it, and that's during a solar eclipse. when the moon covers up the sun and it's like midnight. And then you can see how the starlight behaves. Well, I have a little sort of cartoon here just to show you how that works. And I have a laser pointer here if I can remember how to use it. Okay, if you have a star over here and there were no effect of the sun on its rays, then it would just go straight by the sun as if nothing happened. If, on the other hand, it were bent, it would go sort of like this. Now, this drawing, even though I had 4 years of mechanical drawing in high school, somehow I didn't quite get things in proper proportion. And the distance from the sun to the Earth here, 1 astronomical unit, seems a little bigger than the distance to stars, which is much, much further away. But that doesn't hurt the principle. Now, what Einstein's theory predicted is that this starlight would appear to come from over here. Even though the star was here, the rays would get bent on their way to the Earth, so the Earth observer would think the star was over here. And this is the angle at which the rays would be bent. And according to Einstein's theory, this bending would be proportional to the mass of the sun, and the formula is given here in terms of the gravitational constant, the mass of the sun, the speed of light, and the distance of closest approach of the light ray to the center of the sun. So the closer the light ray gets to the center, the smaller d is, and the bigger this angle is. Now, according to Einstein's theory, this angle would be 1 3/4 seconds of arc if the ray just skimmed the limb of the sun. That's his predictions. Newton's, being half as large, would be 0.875. Now, what is 1.75 seconds of arc? Is that a big number or a small number? It's actually very small. How can I illustrate it to you? Suppose I took a penny and moved it a mile away from you. Then the angle from one side of the penny to the other that you would see is in second of arc. So it's pretty small. You know, a penny doesn't look too big when it's a mile away from you. Okay, so that's sort of the prediction of Einstein's theory versus Newton's theory. Now, how do we actually conduct such an experiment? Well, we do things during a solar eclipse, as I said. And what happens during a solar eclipse? The moon is in front of the sun, and then if Einstein were right, the stars which would have appeared to be in these positions where the black dots are would in fact appear where the red dots are. And so if we took a picture of these stars when the moon was in front of it, the photographic plate would register the stars as being in these locations, the red locations. Okay, that's fine, but what would it have looked like if the sun weren't there to change the direction of the rays? Well, one looks some months later and one sees where the stars really are, so to say, with the sun not there, and then one gets a picture like this if Einstein is right, and you can actually do this experiment and see whether the predictions of Einstein were right, Newton were right, or something else. Now, actually, I said we made these measurements with the sun not in the way, say 6 months later, after the solar eclipse. Why didn't I say do it 6 months earlier, before the solar eclipse? There's a very good reason. It costs a lot of money to make, at least in those days, it cost a lot of money. Suppose you made the observations before the solar eclipse, and then the solar eclipse was clouded out, can't see stars through clouds, you'd have wasted all that money. So I want to see if the original measurements are successful before you go to the other, to the comparison measurements. Well, this idea of Einstein's, that is the prediction of Einstein's, came about in 1916. Those of you with long memories might remember that there was a world war going on. And in fact, Britain was on one side of the war, and Germany, where Einstein was on the other side of the war. Nonetheless, science transcends everything, and through the intermediary of Dutch people, English people heard about Einstein's theory. And in fact, they were aware that there was going to be a very good solar eclipse in 1919, 3 years later. At this time, there was a very famous astronomer in England, Sir Arthur Eddington, and he was having trouble with the establishment in England, in the sense that the English establishment were all behind this war. They were sending English young gentlemen over to France who'd get killed in trenches, and then they'd send over another wave, and so on and so forth. And Eddington was a pacifist. He didn't like any of this, and he was causing a lot of trouble for the establishment in England at that time. And they didn't want to put him in jail objecting to the war, because that would be unseemly to put one of them in jail, you know. Well, he got interested in this eclipse, but it cost a lot of money to carry out an expedition. You'd have to go to Brazil or West Africa where the eclipse was visible. So the establishment quickly gave him the money so that he'd be occupied preparing for the eclipse and wouldn't bother about how many English people were getting killed in the trenches in France. So that's how it all went very smoothly. The war actually ended in 1918. And then in 1919 came the famous eclipse expedition led by Eddington, and they had two expeditions, one to Sobral in Brazil and one to Principe off the west coast of Africa. The reason they went to two places is to double their bets, so to say. In case one was clouded out, they had the other one to go to. Well, in fact, Principe was overcast, but the weather was, but nonetheless, the clouds cleared for a few minutes and they were able to take a few pictures. The weather was perfect in Sobral, and lo and behold, they got results which seemed definitely to be more in keeping with Einstein's prediction than with Newton's, which, remember, was half as big. So that was a major event in world history, although to Einstein didn't make much difference. When he heard about it, he said, couldn't have been any other way. God wouldn't have had it any other way. But the newspapers picked it up, and it made page 8 of the London Times. It couldn't have made page 1 of the London Times. Does anyone here know why it could not have been page 1 of the London Times? In those days, the London Times had only personal announcements and advertisements on the first page. Can you imagine that? No news at all. It was only relatively recently that they abandoned that tradition. You know, the English are very big on traditions. I hope there are no Englishmen here that I'm insulting. Anyway, as you can see, even though it was on page 8 and next to an article on the output of coal and its price with the miners meeting ministers, things don't change. But on the right, you see it's called A Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown. It was generally accepted that the observations were decisive in the verifying of the prediction of the famous physicist Einstein, stated by the president of the Royal Society as being the most remarkable scientific event since the discovery of the predicted existence of the planet Neptune. The English had a hand in that too, and that's why they call that one out. One more objective person might have pointed to other important things, but never mind. In fact, even their own James Clerk Maxwell, but never mind. Okay, if you go down by the article, it keeps waxing eloquent. And then at a certain point in the article it says, it is interesting to recall that Sir Oliver Lodge, speaking at the Royal Institution last February, had also ventured on a prediction. He doubted if deflection would be observed, but was confident that if it did take place, it would follow the law of Newton and not that of Einstein. So, but let's persevere and read the rest of the article, or at least a part of the rest of the article. At this stage, Sir Oliver Lodge, whose contribution to the discussion of this Royal Society meeting at which these results were announced had been eagerly expected, that is, his contribution had been eagerly expected, he left the meeting. So if you're not a good archaeologist, you might abandon the story there. But if you persevere and go to the next day's edition of the London Times, you see there are more articles under the same heading, The Revolution in Science, Einstein versus Newton, views of eminent physicists. And here you say, the subject was a lively topic of conversation in the House of Commons yesterday. And Sir Joseph Larmor, who actually was a physicist, Fellow of the Royal Society, Member of Parliament for Cambridge University, on arriving at a lecture before the Royal Astronomical Society last evening, said he had been besieged by inquiries as to whether Newton had been cast down and Cambridge done in. See, Newton was from Cambridge. You see how they're interested in the science, you know, that's clearly captures their imagination. Anyway, you move further down, and lo and behold, this is the next day, remember. And under the ether of space, Sir Oliver Lodge's caution, to avoid misunderstanding, permit me to explain that my having to leave the meeting reported in your issue of today, Friday, was due to a long-standing engagement and a 6 o'clock train. In England, the trains always ran on time. Anyway, news finally crossed the Atlantic. And the New York Times picked it up, and look what they did. They put it on page 6, even though it was several days later. And they go on to, you know, talk about it, hailed as epic-making. British scientist calls the discovery one of the greatest of human achievements, et cetera, et cetera. So it was quite an event in history. And in fact, it resulted in Einstein being the only scientist up till that time, and none ever since, to have gotten a ticker tape parade down Broadway in New York City. And in fact, he became a household name after that, such that when I was born and grew up as a little kid, the word Einstein to me, I didn't know it was a real person. I just thought it was a word for genius. Anyway, every day for the next few weeks, the London Times had an article, at least one, on the subject of this great discovery. And Einstein himself entered the act on the 14th of November, writing a letter to the London Times. I won't go through the whole thing. It's actually quite a neat letter. But he comes to the end. A final comment. The description shows his sense of humor. A description of me and my circumstances in the Times shows an amusing feat of imagination on the part of the writer. By an application of the theory of relativity to the taste of readers, today in Germany, I am called a German man of science, and in England, I am represented as a Swiss Jew. Remember, the war was just ended between Germany and England. If I come to be regarded as a bête noire, the descriptions will be reversed, and I shall become a Swiss Jew for the Germans and a German man of science for the English. Anyway, I'm sure you all know what Einstein looked like, but I blew that line. I had a joke prepared, but I screwed that one up. Anyway, here's a picture of Einstein and Eddington in a later date in 1931, well after he became a household word and he was totally ignored. But that's how things go in the world. Some people's fame lives forever and others dies almost before they live. Okay, so what's all this got to do with gravitational lenses, you might ask? That was a funny story and all that, but what has it got to do with gravitational lenses? Well, the modern part of our history we'll now go into, which deals with that part, with that aspect. Nothing much happened as far as gravitational lenses. They weren't really discussed much in the literature, in fact, not at all. And then came 1936, almost 2 decades later. And some Czech engineer kept bugging Einstein to do a calculation because he thought maybe if mass bent light, and it seems to, maybe you could form images and use masses as lenses. And he asked Einstein to do a calculation to see whether that was true or not. And Einstein sort of did it over, a few minutes. And he dashed off this little letter to Science in December of 1936. And he pointed out that, in fact, if you had 2 stars lined up, one behind the other, then the one in the foreground would act like a lens. And in fact, if they were precisely lined up, the one in the background would appear as a ring if the light from it wasn't drowned out by the light from the foreground star. And he showed another very interesting fact, that the intensity of that light, that image that was formed, would actually be greater the further away you were from the lens. You go back further, and the damn thing looks brighter, quite contrary to common sense. But this is what he concluded in the bottom of his article, that the observer not only does not see this decrease, but even sees an increase proportional to actually the square root of the distance as you move away from the lens. Well, this is all neat. Now, let me show you a sort of cartoon describing that in pictures, what Einstein described in equations. Let's look at what would happen in two cases. Let's look at the symmetric case where we have a lens, which could be a star or a black hole or any point-like massive object, and we have a star behind it with the light bent by the gravitational effect of this lens so that the path of the light goes like this to the observer over here. And in the symmetric situation, there'll also be a ray that'll come there this way. So we'll have, and in any other dimension, that is, if we went out of the plane, we'd go out in the same way, so that this diagram, which is in two dimensions, if we rotated it about this line, just rotated that diagram, that would constitute this ring that Einstein said one should see, and this is an illustration of how that would go. If we went off-center and put the star over here and the lens over here, then we get one ray coming from the star to us this way with a very little deflection, and another ray coming this way with a very big deflection. Now we can show that in this case, this kind of case, there are two and only two images that you'll see. Here you saw a ring, but here you'd only see two images, no matter how you change this geometry from this symmetry arrangement. I won't take you through all the mathematics. There is no point. I maybe will show you just one neat little geometric drawing that you can make to tell you where the images will form. You have two things to satisfy if you want to see an image. One, the deflection has to be in accord with Einstein's law, and two, the ray actually has to go from the star to the observer. Now, if you put those two constraints together, you get a diagram like this. The Einstein law of deflection goes like this. When you're very close, when the ray is very close to the lens, you get a big deflection. When it's very far away, you get a little deflection. It's sort of like a hyperbola with two components, whereas the geometric constraint that the ray that goes from here out has to come into here is a linear one, and the intersection of these two hyperbolae with a straight line is always 2 points. No matter what straight line you draw, you're always going to have it intersect those two hyperbola and 2 points. Okay. Now, let me go over here and show you an illustration of that. I actually brought in a distant star. It's a little model of a star, but I can't carry that much. So let's turn on the star. And here we have a black hole. This was really rather heavy. It made a hole in my pocket. But anyway, I managed to get it here. And over here we have your eyes, or a substitute for them, the TV. And lo and behold, I arranged this beforehand and had it set up so that the distant star is right behind this black hole in line with your eyes. So you see a perfect Einstein ring. Now you're supposed to applaud. That's to make me feel good for having set it up so well. Okay, now what happens if I destroy the symmetry? If I destroy the symmetry, I should get two images, not one ring. And watch what happens when I destroy the symmetry. You get two images. And they just move around as we change the geometry. Okay, so that takes care of Einstein's no more TV for a while. You can go back to watching Sesame Street. Okay? Uh-oh. I goofed. We're in for some trouble. I moved the lamp. I'm not supposed to disturb stars. It's actually not so easy to disturb stars, but unfortunately it's all too easy for me to disturb this. Okay. So that's the situation with Einstein. Let me ask you a question. When the eclipse, we took the picture of the eclipse of the sun, remember? We only talked about one image of each star. And yet here I've demonstrated, and Einstein demonstrated a little before me, like 60 years, how come we don't see a double image of every star behind the sun? Why do we only see a single image? But remember, if you don't have exact symmetry, what happens is, let's look. Let's put it the right way up. And I can turn this on again. What happens is this ray that comes directly is bent a little, but the ray that comes the other way has to be bent an awful lot. And in order to be bent an awful lot, the ray has to pass close to the lens. But it can't get below the surface of the sun. And in order for us to see the second image, the ray would have had to come closer to the center of the sun than the surface is. And it can't do that. So that's why there's only one image. But with a distant star, you don't have that problem. You only have it because the lens, the sun, is so close to us. When the lens is far away, you don't have that problem. Okay. Now, what happened next? Next, remember, Einstein's article appeared in December of 1936. Early in 1937, an article appeared by Fritz Zwicky, who was an astronomer who was literally always 50 years ahead of his time. Einstein, in his article about the gravitational lenses, stars acting as gravitational lenses, had concluded, and I neglected to point it out to you, that the chance of seeing a gravitational lens, the chance of seeing one star behind another, even if the light from the front star didn't blind you altogether relative to the distant one, that the chances of that happening were so remote as to make this irrelevant. So one shouldn't even worry about gravitational lenses. Nice theoretical idea, sure, but forget it. But Zwicky, as I said, was 50 years ahead of his time, and he realized that a star behind a star, that's improbable. However, a galaxy behind another galaxy, that was more likely to happen. And in fact, he didn't think things through completely in his article, which just appeared in January, a month after Einstein's. But then he came back 2 months later. They published things rather quickly in those days. It's quite impressive how things have improved with time. And in his later article of March 1937, he concludes that finding such gravitational lenses will be practically a certainty. In other words, you don't have to worry about it's never happening. It will definitely happen. Okay, that was 1937. Great. What happened next? Absolutely nothing. It made about as much impression among professional astronomers as Carl Jansky's discovery of radio waves from the Milky Way did in the same period of time. One might get the feeling that professional astronomers don't catch on fast. But once they catch on, then they really take off, and you have to watch out. Okay, now Fritz Zwicky, you remember, talked about galaxies acting as lenses. Well, galaxies are different from stars. Galaxies, of course, are composed of stars, but galaxies are mostly empty space. There's quite a big distance, even here to the nearest star. You don't just walk over, it takes a few days to walk to the nearest star. Well, so most galaxies have nothing in them, so they form a different kind of gravitational lens from what a star or a black hole forms. You might call them transparent gravitational lenses, because instead of having an object here that's hard and, how shall I put it, opaque, I should say, you have something that's mostly transparent. So now you can not only get, in the symmetric geometry, you not only get this ring from the symmetry, remember about this axis, you can just revolve around this axis and you'll see a ring, but you also get a light that comes directly from the star to the observer. Now there's one difference. This light that comes directly is not magnified. The light that goes this way, as you can show from the arithmetic, is magnified, looks brighter, but this one doesn't look brighter. So you'd predict that you'd see a bright ring and a little dim spot in the middle if you looked at a star or another galaxy through a foreground galaxy. Now if you have an asymmetric situation as before, you may also get 3 images. And in fact, using the same kind of geometric argument I showed you before, now the Einstein deflection law, instead of looking like this as it had before, since there's no deflection at the center, not a maximum deflection, but no deflection as you go through the center, this deflection law turns around and goes through the origin and comes back. Now, with the geometric constraint, you have various possibilities. You can have now 3 images, not 2, but 3. Or if the geometric constraint line were, say, to lie down here, you'd get no images. Or if it were to go through this point and then there, you'd get one image here and 1 image there. You had 2 images in this tangency case. So there are all sorts of possibilities, as was soon realized. Now we go back here. Not only did I bring in my star and black hole, but I brought in 2 galaxies. And here's the first galaxy. It used to be called a star, but we're very flexible. Unfortunately, so flexible I moved it, which might turn out to haunt me, but let's see. Okay, now that was the black hole star. Now somewhere here it is. I have my galaxy. And let's see if it's still lined up. This is supposed to be lined up in the symmetric orientation. Now I'll let you open your eyes. Well, not too good. Let me see if I can rearrange that a little bit. I hope you can all see that there's a nice bright ring and a dimmer spot in the middle. That's the symmetric situation. Now let's move off from the symmetry situation, and you see we have 3 images as predicted, but watch what's happening to the central image. What's happened so far? It got brighter, and it's going to get brighter still as it moves off. And then finally, it's going to merge with that one and then disappear altogether, although it's disappearing now for not the reason that I was showing you there. It's run out. Unfortunately, this galaxy cuts off. Okay, so that's the end of this demonstration. And now you'll have to close your eyes and start listening to Sesame Street again. Okay, so now you all know, how I knew I'd trip up on something here. How gravitational lenses work. And we can move on, except for one thing. I will, for some of you, show how it's done. I mean, most of you probably realize those weren't stars and galaxies. So how did we make them act like stars and galaxies? Well, we had to make out of plastic something that had the same effect as massive galaxies and stars would have. And I just thought I'd give you a little view of the cross-section. The black hole, or the star, is a lens that looks like this. It comes to a cusp here. That's like the heart, the black hole of the star. And it has a particular curvature here to mimic the Einstein deflection law. Remember, here's the Einstein deflection law now in yellow. It was red before. And here in blue is the deflection law for this particular realization or match to the Einstein law. Here is a similar thing for an attempt to imitate the galaxy, and the shape looks like this, but it cuts off here, whereas the actual deflection continues on both sides. The equivalent mass of the model is about equivalent to a black hole, about 1/10 the mass of the Earth. Just to give you the scale of things. So if we use plastic instead of mass, we can do everything that 1/10 of the mass of the Earth could do. Okay, let's move back now to our historical discussion. We're up to the end of modern times, Refstall. But first, let's just say, as I indicated, nothing happened after Zwicky's saying it was an absolute certainty that we'd find gravitational lenses among galaxies. So, nothing at all happened. There was no theoretical interest. There wasn't a single other paper on the subject. There wasn't any observational searches for gravitational lenses. Here, this amazing prediction, and nothing happened. That was 1937, 1947. By then, nothing happened. 57, nothing happened. It wasn't until 26 years later when someone looked at the subject theoretically, and Refstall came along and did a very nice job of going further than either Einstein or Einstein or Zwicky had gone. And he added a new element to the story, which I want to emphasize now. And that was, what he noted was that if you have rays coming from, say, the distant galaxy to us, forming two images, the time it takes the light to go along one image will be the same as the time it takes the light to go on the other image if we have a condition of symmetry. But if, as most often would occur, you don't have symmetry, then there'd be a difference in the time it takes the light to go via one path than via the other path. And that's the key to the title of this talk, how we connect gravitational lenses to getting the size and, in fact, the age of the universe. Huh? How's that work? Good question. I'm glad you asked. The point is, and this is a little bit of a complicated story, and I will try to make it intelligible without going on for too many more hours. The universe was discovered in the 1920s to be expanding. Okay? So the universe is expanding. If we know how fast it's expanding, and we know the distance to an object, then from the combination of the velocity and the distance, it's not hard to figure out the time that it has been expanding, or the age of the universe. Or if you had the distance, you could then, if you could relate this, if you could have the distance and the velocity, if you had the distance, you know the size. If you have the velocity and the distance, then you know the age. Okay. How do you get the distance to galaxies? It took us hundreds of years to figure out how far the sun was to any appreciable accuracy using measurements and units that we have on Earth. It's a devil of a problem. A star is enormously further away from us. The nearest star even takes light 2 1/3 years or so forth to get from the nearest star. It takes 8 minutes to get from the sun. When we go to other galaxies, it can take hundreds of millions of years for the light to get to us. So trying to figure out how far away they are is not easy. However, the gravitational lens gives you some handle on it. It's not the whole story. The whole story has one more step in the logic, which I'll get to in a few minutes. But let me just get this one point across. The time it takes light to get to us will depend on the distance. The further away, the longer the time. Okay, so the time delay, or the time it takes light to get, is directly proportional to the distance. So is the difference in the time delay along the two paths. The difference in that time delay is also proportional to the distance. And it's that difference that we have a possible handle on through gravitational lenses, and hence a possible handle on the distance. So that's the connection with the title. But still, this is all theory, right? We're in 1964. We're all theory. We don't have anything to observe. Okay, so now let's move to current events with one other remark. Ref Stahl's article set off a cascade of theoretical articles. The number of articles, which had been 0 between Zwicky in 37 and Ref Stahl in 64, suddenly took off. So there were lots and lots of articles in the journals. But no one was looking for any lenses. Okay, it's all theoretical articles. Nobody observed anything. But then along came a person who was doing a radio survey in England. And he was just cataloging all the radio sources that he saw with a particular telescope roughly near the North Pole. And then a colleague was charged with the problem of finding out which optical objects corresponded to these radio objects. Well, if there's only one optical object nearby, you could pretty well assume that they were associated if you made your measurements accurately enough. But in the case of a particular radio source, which is fondly known as 0957, after its plus 561, of course, after its position in the sky, and there were 2 objects there, A and B, they were 6 arc seconds apart on the sky. Remember what an arc second is? It's a penny at a mile. So this is like a $50, well, it's even more than a silver dollar at a mile, okay, apart. But the radio survey that looked in this region wasn't able to tell where the things were to a circle about like this. So they didn't know whether this corresponded to the radio source, this corresponded to the radio source, or something else. So it being very cloudy in England, this fellow came to the United States and used telescopes in the United States to observe these 2 objects to see if he could get a clue for which one might be the radio source. And let's see. And one of the telescopes used to make the initial spectra, or that is to look at the light from these optical objects to see what they might be, was the multiple mirror telescope in Arizona, which has 6 individual telescopes all collecting light, and it's very good for this kind of observation. One thing I neglected to figure out is how do I turn this off? I can go forwards and back. I go backwards, but that won't work in the future. So I have a problem. Somebody's going to have to help me. I try to think of everything ahead of time, but I missed on that one. Anyway, okay. So he looked through that telescope, among others, and came up with what's called a spectrum of light. Now, what is a spectrum? A spectrum is you look at how much light you get as a function of color. You break the light up into its component colors, and you see how bright it appears at the different colors. And lo and behold, you look at this A object, and its spectrum looks like this. That is, it's brightest here, next bright here. And you look at B, and by God, it's brightest here, next bright here, and they line up beautifully. And you see this scruffy bump here. Well, maybe it's that scruffy bump. It's not, it's not what we call high signal to noise, but it's clear that at least something in common. Okay? So that was good indication, or at least it was to these people, that maybe these A and B were 2 images of the same distant quasar that was discovered by the radio radiation. So that was the hope. And that, I might point out, that discovery was made by some, well, how shall I put it, by some astrological coincidence on virtually the 100th anniversary of Einstein's birth, within 2 weeks. So if you kept the Russian Orthodox calendar for one of them and our calendar for the other, they would have been exactly coincidence. I just invented that one on the spot. Okay. Anyway, so now what I want to do is go quickly through the case history here of this particular object, 0957, which some of us call, just to be friendly, just 0957. We don't bother with the full title since there's nothing else in that part of the sky that anybody worries about. So let's look at the basic evidence that it's a lens Then we'll look at the ogive clue, and you don't have a clue as to what I mean by that, but you will. Then we'll look at the radio view, and then the time delay race, then the mass distribution criticality, the degeneracy enigma, I'll probably have to skip that, Hubble's constant, the size, scale, and age of the universe, and the inevitable problems that I gave you a little foreshadowing about in the beginning when I told you that we're not going to finish the history here. I fear, however, I may not even finish all my talk because I can't quite see that clock, but it looks like I'm in danger of outliving my welcome here. So I'll have to speed up. By that I mean not talk at 10 times the speed of light or speed of sound, but just leave some things out. Okay, so that was the optical situation, and just at that time, by another queer coincidence, the VLA, the premier instrument at the moment of the National Radio Astronomy Observatory, was just coming online. And Bernie Burke at MIT had heard about this discovery of Walsh and his co-workers of this potential gravitational lens. He was intimately involved with the VLA. He immediately sent off a telegram asking for time to look at this object with higher resolution than was possible with the radio telescope that discovered it. Now let me go forward and give you a view of the VLA, which is out in Socorro, New Mexico. And next time you're passing by in Socorro, you must drop in. It's one of the 10 wonders of the world. It has 27 telescopes on 3 arms. It wasn't fully instrumented at 1979 when Bernie Burke went and had this instrument take a radio picture with high resolution of these 2 objects, and here's what he found. Here are the 2 objects, the B and the A, and here it's clear that there's something else, looks like jets or something coming out of this, but no indication of any images of these things over here. In other words, there are 2 images, but some of this stuff has only 1 image. But you may remember, if the geometry is a certain way, you would expect only 1 image, not 3 images, or 2 if you had tangency. Well, this looks like a case of 1 and 3. Anyway, that was the situation. But what are we missing? What are we missing? Here are the images, okay? Say, just concentrate on these. We're missing the lens. The lens is supposed to be closer to us. Why are we not seeing the lens? Well, people thought the lens was probably in the middle because these 2 images are roughly equally bright, a little 4:3 ratio, but they expected the lens to be right in the middle. And they didn't find anything in the middle. They looked deeper. They exposed their plates longer. Nothing happened. Then along came Stockton in Hawaii, where the seeing is very good. That is, the images don't shimmer. And he took a picture, which is illustrated. Whoops, I went the wrong way. I'll figure this out yet. Okay, here's the ogive clue. What we have here is the A image as it appeared. This is not really the object as it exists really in the optical. This is a combination of seeing and imperfections in the telescope, which makes it a shape like this. Now what he did, and here was the image that he saw for B. Now what he did was say A and B should be the same except scaled a little differently. So he scaled A, subtracted it from B, and got this. So this is the ogive clue. He subtracted this ogive from this, not quite ogive, and here is the lens. The lens was obscured by the image B. It's so close to the image B that you couldn't see it. And that was a major discovery. We have the smoking gun, the lens. Now, the VLA got better and better, and Bernie Burke went back to the VLA, and lo and behold, with the VLA a little better, now you see the lens in the radio as well. And in fact, more clearly separated than in the case of the optical picture. Can we turn off the slides for a moment? Thank you. Okay, so now we're really making some progress, but still we're not really positive that it's a lens. So what we did was then look with even higher resolution, with the resolution 1,000 times higher than in the previous picture, 1,000 times higher. So we could look at the very heart of that little speck that you saw. And here's what the heart of that speck shows when we look with this other technique, which I don't have time to explain, which involves radio telescopes disported around the world, and we have the resolution equivalent to having built a telescope the size of the Earth. Well, I'm only exaggerating slightly. Anyway, here's what we see. In the A image, we see this. In the B image, we see that. And boy, do they look alike. And in fact, one can make detailed comparisons, and they're just the sort of relationships that one would expect for gravitational lenses. So that really clinched the case for this being a gravitational lens. Now, how do we get from there to the size of the universe? Okay, let us move and talk a little bit of the relevant math, which I mentioned orally to you, some of it, a few minutes ago. First, the point is we have distance in the universe is proportional to velocity. When you have an expanding universe, the things that are furthest from you are moving fastest away from you. If you took a balloon and blew it up, the specks near you would move slower relative to you, move away from you slower than the parts further away until you got around the other side. But in your area, the expansion, if it's uniform, the expansion would, the distance would be proportional to velocity, or vice versa, velocity is proportional to the distance. The constant of proportionality in this relation, which is unknown unless we can measure distance, and in fact measuring distance gives us that proportionality constant, because velocity is easy to measure. Velocity turns out to be very easy to measure. We use this thing called the Doppler shift, and I don't have time to go into it. If you know what police radars do to tell you how you're speeding, well, it's the same kind of thing you can do to tell how galaxies are speeding, except they're slowing down. But anyway, it's the same principle. Now, the time delay, the time it takes the light to get to us, is also proportional to the distance. Therefore, the time delay is proportional to h naught. But this constant of proportionality between the time delay and this measure of the size of the universe depends on the lens's mass distribution. So we have two things we need to do in order to get h naught. One is to measure this time delay, and two is to measure the mass distribution of the lens, which determines how much bending there is. So h0 is, by this way of looking at things, the size scale of the universe, and its inverse is approximately the age of the universe, by the argument I went through orally a few minutes ago. Well, maybe it's more like half an hour, but something like that. Okay. So how do we get the time delay? If the distant object being lensed just puts out a nice uniform beam of light like this spot here, and it just keeps on putting it out, we could see this spot in two images, but we'd have no marker to tell us when the light left, so we'd have no way of knowing how to compare the time of arrival via the two images. However, if the light from the quasar had a glitch in it, that is, it changed intensity, it changed brightness from nothing to something. At a certain time, we'd see it in image 1 at a particular time, and then image 2, if it took longer to go on image 2, we'd see it later. And this difference will be, the difference in the arrival of seeing that glitch in the two images will be the time delay. Of course, nature isn't so kind. It doesn't give us nice variations like this. It gives us more variations like this, which were measured at the VLA by Joe Lehar and Bernie Burke and Jacqueline Hewitt and a number of others at MIT over a 10-year period, also, as I said, on the VLA. And the curves look rather herky-jerky, and it's hard to tell exactly what the difference in the time delay is from those variations. In fact, optical people also made measurements, and in truth, they disagreed. The optical people claimed that the time delay traveling the two images was 1.1 year with an uncertainty of only 3/100ths of a year. The radio people thought it was 1.4 years with an uncertainty of only 1/10 of a year, and we had a disagreement. It's like we had a railroad being built by astronomers. and they didn't quite line up correctly. So it took a theorist to come along and tell them how to put the tracks back together again and analyze the data in a more sophisticated way, and showed that, in fact, the radio people were right and the other people were wrong. We won't mention who those other people were. Okay, so now we have the time delay, and all we need is a measure of the mass, and we're home free. But the mass is rather tricky to measure. And the reason is based on these measurements of the images of the gravitational lens. And the reason is a tricky one, and I'll try to do it very quickly. The reason is you don't know what the lens looks like. You don't know what the source looks like. You only know what its image looks like. The source could be different. And we can't tell the difference between, in this trivial example, nothing between us and the source, or a flat, transparent lens and a smaller source. In other words, this will magnify a smaller source and make it look exactly like a larger source would have looked without any magnification. There's no way we can tell the difference. And I could show you more sophisticated examples, but that's the basic idea. We can't tell the difference. So what can we do? Well, we have to have another approach. And the other approach, if I can only find it, hold on for a few minutes. I'm almost to the end, but I can't find that other one. Just a second here. When you try to skip things to go faster, sometimes you go slower. Oh my. Yeah. Oh, here it is. I had taken it out all along. Okay. More math. I'm sorry. The observations of the images alone cannot yield this mass, as I said, because of that basic degeneracy. But we can use other measurements, such as the velocity spread among the stars in the galaxy that forms the lens, to infer the mass of the galaxy by something called the virial theorem, which most of you have never heard of and probably never will other than this lecture. Basically, it's a way of telling from the velocities how big the mass is. And that's like from the planets, from how fast the planets go around the sun, because of Kepler's laws, which maybe some of you have heard, you can infer the mass of the sun. It's the same kind of thing you can do here. And we developed a nice simple formula that tells us how this measure of the size of the universe can be determined in terms of this time delay and in terms of the spread and velocities of the stars in the lensing galaxy. And in fact, if we use measurements recently made, we get an answer. And we get an answer that says that h0 is like 40 kilometers per second per megaparsec, which I won't go into, but it's a measure of how fast things go as a function of distance. And the inverse gives you roughly the age and shows the age of the universe is of the order of 20 billion or so years. And that's nice and comforting because at least it makes the age of the universe older than the age of the Earth and things like that. So it's very comforting. But is it right? Well, if I thought it was right, obviously I wouldn't have done that, right? So it's not clear that it's right. There are too many holes in the argument. So I'm going to have to leave the story roughly here, but let me say what we can do as prospects for improvement. We can look deeper and more often and see other things in the same field that might be imaged other than this quasar, and that will give us more information on the mass distribution. We can look at more sophisticated models. We can also try other lenses, as we must do in any case, because you never trust one example in astronomy. That's a definite no-no. Okay, so let's look at some of the other lenses we could look at. And for example, very recently, the last couple of years, we've discovered things that look almost exactly like an Einstein ring. You see, this is a radio map, again made at that great place, the VLA, and you can see radio radiation almost all the way around. And looks very close to an Einstein ring. And here are two images of something else and placed one outside the ring and one inside the ring, just as you'd expect from a gravitational lens. And I just have a couple of more here's another illustration of that same lens from the VLA, and a final one of that same lens from the VLA at the highest radio frequency used, and you can see a lot of detail, and it was this that was chosen for the poster. Now, there are a lot of people who break into two camps: the gung-ho types who say gravitational lenses are going to answer all the questions that we'll ever want to know the answer to in astronomy. They have the holy grail, they'll lead to everything. And there are the pessimists who say, yes, for every new measurement you make, every new great idea you have, there'll be 79 complications that will prevent you from reliably deducing anything of interest to anybody. And those two countervailing views, to which astronomers roughly divide, are illustrated very nicely in this next slide of Escher's, where you have angels over here and devils, and you can, if you use your eyes properly, you can switch between the devils, seeing only the devils, or seeing only the angels. And that's a perfect description of how astronomers view gravitational lenses. And let's kill the slide now. Thank you. Okay, we're almost finished. I wanted to just say a couple of more words. First of all, it is clear that gravitational lenses are here to stay. It is definitely a field that has made its mark and that will continue. And how can I be so sure of that? Very simple. 2 books have already been written solely devoted to gravitational lenses. And that means for certain there'll be lots of students who will use those as textbooks, and the field will go on forever. One thing is also clear, that we need new ideas. However, there's one problem. The time scale between getting a new idea and obtaining the funding to be able to do something about the idea is rapidly approaching the lifetime of the average human being. So it is clear that the good ideas of the future will have to come from the very young. And so what I did was made a special mission. I took it as a special mission to locate the young people whose new ideas would set science for the future. And I wanted to share with you, in closing, a picture of some of those people. Thank you.